In this section, we are going to study the testing of the hypothesis for standard deviation of normal population. So, in this case, we are going to test the hypothesis H naught sigma equal to sigma naught, where sigma naught is a value suggested theoretically or by experience, and to test the equality of standard deviation of two normal population, that is H naught sigma 1 equal to sigma 2. The tests are developed for both small and large sample. First, we consider the hypothesis that H naught sigma equal to sigma naught, that is sigma naught has a specified value. Since the sigma naught cannot take a negative values, the alternative hypothesis for this test is always H1 sigma greater than sigma naught. So, first consider the case of small sample. Let a sample of size n be taken from the population and let S be the standard deviation of the sample. To test the hypothesis H naught sigma equal to sigma naught, we use the chi-squared statistics, chi-squared equal to n squared by sigma naught squared, which has chi-squared distribution with n minus 1 degrees of freedom. The rejection rule is reject H naught if actual chi-squared greater than or equal to tabled chi-squared alpha, which is corresponding to n minus 1 degrees of freedom. Here we give two examples. The first one is a direct example, and the second one we have to calculate the sample standard deviation from the values given. So the second case, in the case of large sample, let the sample of size n be taken from the population and S be the sample standard deviation. Then to test the hypothesis H naught sigma equal to sigma naught, we use the Z statistics, Z equal to S minus sigma naught into root of 2n by sigma naught, which has standard normal distribution. And the rejection rule is reject H naught if actual Z greater than or equal to critical Z alpha. So two examples are provided. Now we consider the testing of hypothesis regarding the equality of two normal population. That is, we are going to test the hypothesis H naught sigma 1 equal to sigma naught. Again is the alternative H1 sigma 1 not equal to sigma 2. So for the small sample case, let S1 and S2 be the standard deviation of sample of size N1 and N2 taken from two normal population. Then first we calculate N1 S1 squared by N1 minus 1 and N2 S2 squared by N2 minus 1. The statistics is the ratios of these two quantities, with the bigger of the two being taken as the numerator. And this ratios follows F distribution. If the first one is bigger, then the test statistics is F n1 minus 1 n2 minus 1 equal to n1 n2 minus 1 s1 squared divided by n2 n1 minus 1 s2 squared, which has n1 minus 1 n2 minus 1 degrees of freedom. And the second one is f n2 minus 1 f n minus n1 minus 1 equal to n2 into n1 minus 1 s2 squared divided by n1 into n2 minus 1 s1 squared, which this has a f distribution with n2 minus 1 n1 minus 1 degrees of freedom. So the rejection rule is reject H naught if actual value of f is greater than the tabled value of f alpha. Here we are given two examples. So the first example, the ratio n1 s1 squared by n1 minus 1 has the bigger value, and the second example, n2 s2 squared by n2 minus 1 has the bigger values. And please go through the examples, how f is calculated and how the degrees of freedom is obtained. Finally, for the large sample case, to test sigma 1 equal to sigma 2, we take two samples of size n1 and n2 from the given two normal population and let s1 and s2 be the standard deviation of the sample. In this case, we use the Z statistics. Z equal to S1 minus S2 divided by S1 squared divided by 2n1 plus S2 squared by 2n2 square or raised to 1 by 2, or Z equal to S1 minus S2 by root of S1 squared by 2n1 plus S2 squared divided by 2n2, which has standard normal distribution. And the rejection criteria is reject H naught if actual absolute Z greater than critical Z alpha by 2 obtained from the normal table. An example is provided. Some examples are given already and you can go through this. Some more example will be uploaded in the Google class. Please exercise.